All right, let's take a look at our first lesson on linear programming. This one is called Optimization with Linear Programming. And before we start on the process, this first lesson is just really teaching the process. How do we do that? We're going to cover some vocabulary first. So the first vocabulary word is optimization. Optimization basically means that you are optimizing something. You are finding the maximum or minimum value. And in our scenarios, this value, and in many scenarios, the value is really the Y value. That's the quantity that you're maximizing or minimizing. Linear programming is just one type of optimization process. It's just one of them. There are others. We use several different optimization processes in calculus. This is the one that we're going to be working on in Algebra 2. Constraints, a way to think about constraints is, the word constraints, it means something is being constrained, or in other words, they're going to be boundaries. There'll be boundaries. For example, if let's say you want to build, a box of candy. Maybe there's a particular number of boxes that you have. You don't have any more than 20 boxes or something. That would be a constraint on your project, right? You wouldn't be able to do more than that. So there's going to be constraints that are involved. And then the last vocabulary word, it's called objective quantity. This is the equation that describes what you're maximizing or minimizing. And so let's look at, I'm just going to kind of label these things down here. These three inequalities would be called your constraints. And this particular equation, this is your objective quantity. That's your objective quantity. So for the objective quantity, what we're going to do, so this whole let's just talk about the process in general. We're going to graph our inequalities. Let's kind of go back to this lesson right here just to remind ourselves. We're going to graph our inequalities and we're going to locate the solution, the area that has the solution. Like for example here, this is a solution. That's what we're going to do. We're going to graph these. It's going a little crazy, isn't it? Silly thing. We're going to graph those inequalities and we're going to find an area that's bound in. We're really not going to work on unbounded areas in this. We're going to work on bounded areas. And so that's our first step. We're going to find the vertices of these bounded areas, and we're going to take the vertices and substitute them into the objective quantity equation so we can find out what the max or min would be. And that's kind of an overall, look at the process that we're going to do. So first, let's go ahead and graph. So this means that y, so a y equals equation, right, is one that is horizontal. Y is between 3 and 6. So let's draw that between 3 and 6. And it's got the equals lines or equal to lines. So there's 3, 5, 6, there's 6. So we know y needs to be between there, so we're really looking at, and I'm just going to highlight this for just a moment, we're really looking at this area in here. Okay, that's what we're looking at. Now I need to graph our other lines, so let's get rid of that for right now. So that's the first one. On the next one, let's see, y equals 3x plus 12. So let's do this in a different color. We'll do green. So we'd go to the typical way to do this would be to go to the y-intercept of 12 and then do our slope of 3. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we'd have maybe 11 and maybe 12 here. And then our slope is 3, so rise 3, run 1, so 1, 2, 3, 1. 1, 2, 3, 1. Okay, so let's draw that one. And that one is also a solid line. Okay, then we have y is less than or equal to negative 2x plus 6. Now before we leave this one, let's go back and look at this one that I drew in the green. Let's look at this one. This one's green, and this one is the blue one. Let's look at the green one. This means y has to be smaller, so we would really be looking up underneath this line, not above it. So we're not really looking at any area out here. So let's just kind of keep narrowing it down. So we need to be between these two lines, and we need to be under the green line. All right, so let's take a look at the next one. Let's do that one in a light blue. Okay, so the y-intercept is 6, which would be right here, and the slope is a negative 2. So let's draw this one. All right, and so for this one, we want to also be underneath. We want to be underneath. So we need to be under the green one, under the light blue one, and between the two dark blue ones, which gives us this area right in here. Okay, this is our area of interest. And so we want to see the vertices. You recall those are like corners. The vertices of this happens to be a quadrilateral. So here is one vertex. Here is one. Here's another one. So these are our 4 vertices. And let's just number them just so that we can keep track. So we're just going to call this vertex number 1, vertex number 2, number 3, and number 4. Do you have to number them? No, you don't have to number them. I'm just trying to keep track of what's going on. All right, so let's see. Several of these points actually landed perfectly, like they're not fractional, right? They landed perfectly on our, like one of the crosses, like it's an integer. So if we look at this green line, my drawing isn't very good, but if we went down 3 over 1, down 3 over 1, down 3 over 1, see it is right here. So that's an integer. We know number 1 and number 2 and number 3 are integers. Number 4 is not an integer. That's pretty obviously like in the middle. So let's go ahead and write out our vertices. So vertex number 1 is what, negative 3, and that's 3. Vertex number 2 is what, negative 2 and 6. Vertex number 3 is 0, 1, 2, 0, 6. Vertex number 4, we're going to have to do a little work on. We need to actually find that intersection. And you're thinking, my goodness, how are we going to find that intersection? What are we going to do? Well, we need to get the equation of the light blue line and the equation of this dark blue line, and we need to intersect them. We need to set them equal to each other. So let's remind ourselves, this dark blue one, this one was y equals 3. And this light blue one, this one was, and since it's the actual line, it's equals, y equals negative 2x plus 6. So what we need to do is we need to take those two equations and set them equal to each other. So let's do that. So basically we would have 3 equals negative 2x plus 6. So I'd move the 6 over. What would that give me? A negative 3 equals negative 2x. So x is basically 3/2. All right, so I've got the x value of that vertex. Now, how do you think I might find the y value? Well, the y value happens to be 3, right? It's on this this line, that dark blue line. So there's vertex number 4. Yay! So let's go over the process again. We graph the constraints. We determine where the solution is, where it's bound in, this colored part right here. We label the vertices, write them down. Now our last step to optimize is we're going to plug the vertices into the objective quantity and find the max or min. So let's do that. So we'll start with f of negative 3, 3. That's basically vertex number 1. And we plug that in. So that's going to be 4 times negative 3 minus 2 times 3. And I've already worked that out, so I'll save you the arithmetic. It's negative 18. So let's take vertex number 2. That's f of negative 2, 6. So again, we're plugging into this objective quantity. So we've got 4 times negative 2 minus 2 times 6. And that gives us a negative 20. Okay, that one's smaller. So far number 2 is the winner for our minimum. We're finding maxes and mins. Let's do the third one. So that's f of 0, 6, which would be 4 times 0 minus 2 times 6, which would give us a negative 12. Okay, so negative 20 is still the winner for the minimum. The last one, number 4, f of 3/2, 3. So that's 4 times 3/2 minus 2 times 3. And crazily enough, that turns out to be 0. So let's go, they just wanted us to find max and min. So let's go back, let's circle. This one is our minimum value. So minimum. And this one generates our maximum value. Maximum. Another way would be just to write it out. So we would have our negative 20 is our minimum value. And 0 is our maximum value. All right, very good. And that's our very first lesson on linear programming.